All right. Glad we can talk about this. So yeah, we're going to give an overview about how we think about attestation and recovery and where TPM plays a role in that, and some work we've done in the ecosystem to bring things forward. So at a high level, software bugs give us job security. We can't really assume that the software we write does not have bugs. We are human. We're going to write bugs. We fix what we can find, but we need a plan when things go wrong, not if. And there's a lot of code running on these machines that we manage. So what is our plan when things go wrong? Roughly speaking, we release our best effort software. We do our best not to release bugs, but we think we're gonna. So we find the bugs, we fix them, roll out the fixes, and then verify that the fixes we rolled out actually went where we wanted them to go, and repeat. Steps 3 and 4 are separate steps in a data center environment because we are not actually at the machines. There's far too few of us humans to do that. So we package these firmware updates out, we roll them out, and hope they landed. How do you make sure that they landed on these machines that are far away from you? Well, there's a really simple way. You can just ask the machine to tell you, hey, what software are you running? And it'll report some metrics saying, yeah, my BIOS is version X, my kernel is version Y. And that's a fine approach as long as the bug that you're fixing, if leveraged, might cause the machine to start lying to you. And why might it do that? Well, maybe it allows a remote code execution. An attacker can leverage that and start faking out the metrics and saying, yeah, sweet, we're all patched up, but really they're still running the old broken software. The better way is with trustworthy attestations with cryptography to prove that the software that is on the machine is actually what we want it to be. And if not, we can take actions to remediate that. So how do we remotely verify this software? Basically, it's measured boot is the name of the game. Any mutable code or configuration that might affect the trustworthiness of the machine, which is almost all of it, measure it before it runs, and then put those measurements somewhere safe. In this diagram here, we've illustrated putting them in a TPM. That's a common use case for a TPM. A TPM is not required for this, and in fact, for the longest time, Google used their own custom Titan chip, and we still do use our custom Titan chip with a very vertically integrated custom protocol, but it is very much like TPM, and we are moving in that direction. So it's a TPM. And then the TPM can then emit some cryptographic proof of those measurements to some relying party, and there's a whole many talks about how that might work, how you make the policy, how you react to it, et cetera, but really, at its most fundamental, today's talk is about how the TPM proves something to someone else. And in order for any of this to work, the TPM has to keep a secret that no one else knows. So the TPM can say, I'm the TPM, you trust me because XYZ, and I'm telling you the measurements are thus. If a bug in the TPM caused it to leak this secret that it's using to prove things to everyone else, then this entire attestation and recovery flow just doesn't work anymore, because you can't recover from that kind of bug if you can't prove to yourself you're talking to the TPM that's proving things to you. This gets into the concept of a trusted computing base, or TCB. There are many different definitions of this. Here's one working definition. The amount of code you need to blindly trust not to have really bad bugs. You want your TCB to be really small because you want to trust as little code as possible. The smaller amount of code there is in your TCB, the fewer chance there are that there's a really bad bug in there. In this diagram, that the TPM is clearly in the TCB because you trust it to tell you the truth when you ask it. The BIOS is, a bit of a gray area there because in many cases the BIOS just runs before it's been measured. So if there's a bad bug in that BIOS, it can just fake out its own measurements. And the kernel is clearly out of the TCB because we measure it before it runs. But yeah, so TPM's in the TCB. Why is this bad? Can we just live with this? Well, no, the TPM's not magic. It's just a place to run more code. And there's a lot of code in there. You got the command dispatcher, structure marshalling, policy enforcement logic, crypto libraries, etc. It's a wide attack surface. The TPM does a lot of things for different use cases. It's fairly complex. And we don't think that we want to trust all of that code with the keys to the kingdom. This is not purely hypothetical. There have been bad bugs that affected the TPM. A couple of CVEs here, ROCA, TPM fail, bugs in RSA key generation, ECDSA signing, policy checks. We're not highlighting this to point fingers. Like I said, we're all human. We're going to make mistakes. Just got to plan for what to do when those mistakes happen. So how can we reduce the size of the TCB? We don't think we can eliminate it entirely. You got to trust something, but we can shrink it to, let's make our target be just the bootloader. That has a much smaller attack surface than the TPM. It is not responding to external API calls, doing any kind of structure, marshalling, parsing of user content. It's just verifying and launching some firmware. And we'll just call the rest of that the firmware. So how do we remove the firmware from the TCB? What's the high-level flow here? So pictured here is a firmware image, version X, that is really buggy and has leaked all of its secrets. So what do we do about that? Well, first, we update to new patched firmware that doesn't leak its secrets. And then we have to give that new firmware new secrets, which weren't leaked by the old firmware. And then somehow teach the remote verifier not to trust the old secrets and to start trusting the new ones. That's somewhat out of scope of this talk. Now, how do we do this in practice? The goal is to give a unique secret to each version of firmware. How can we do this? Well, let's have the bootloader keep a secret. We're talking about the bootloader being in our TCB, so let's entrust a secret to the bootloader, but not the firmware. The bootloader can measure the firmware. It probably is already doing this because it has to verify the signature on that thing. And then crank from KDF and derive a key for the firmware. As we can see with this scheme, if we update the firmware to a different version, we'll get different measurements and we'll get a different key for that new firmware. So it satisfies the requirements of what we're after here. Okay, so with this scheme, we can now have the TPM firmware have a secret known only to that version of firmware, such that old buggy firmware could not have leaked it. So that's great. However, even if we've introduced this kind of secret into a particular implementation of a TPM, the TPM API as a whole didn't allow us any way to actually use that secret. And to get into why and how we fixed it, turn time over to Chris.
Thanks. Okay, so you could think kind of trivially, we could just make the TPM sort of like change its secrets magically under the hood and say, update your TPM firmware. Now your TPM has totally new keys. But that would be kind of an astonishing and surprising result for someone who's already using their TPM. Like maybe they don't want all of their keys to just go away by surprise. So we need some way of plumbing in kind of an opt-in to this key derivation scheme. Unfortunately, we don't have enough time to explain all 127 commands in the TPM API, but here's a picture of one of them. This command is called create primary. It's the command that you use to create a primary key in the TPM. Which is not a database term, but a deterministic key term. So over on the left here, you can see we've got these three different unique seeds or secret seeds that the TPM internally stores and has access to. These are fed into a DRBG, or really just a KDF. This is an implementation detail of the TPM, so different TPMs can do different things here. But the secret seed is combined with the template of the object that's being created. So a TPM object template includes all of the attributes, all of the rules for how to use the key, the algorithm for the key, the detailed scheme for the use of that algorithm, everything that uniquely defines that key pair or that key. Those are combined in the DRBG, and those result in the primary key. So this command is used to produce the endorsement key. You can use it to produce primary attestation keys or primary sealing keys. In general, it's used to create the endorsement key and the top of any storage hierarchy of keys in the TPM. So these seeds are secret. They are referenced by handles in the TPM API. So we have these 3 different 32-bit values that reference owner, endorsement, and platform hierarchy for the seeds. These seeds don't change when you update the firmware, so neither do the keys, which is great. You fix your TPM, but not all of your stuff breaks suddenly, which is a nice property. So now, thanks to what Jeff was talking about in the first part of this talk, we have this concept of a version unique secret that we'd kind of like to use. We'd like to combine this in with the other inputs to the DRBG to start getting version unique primary keys. So that's what we did. So there are new handle values in the latest version of the TPM spec that on a supporting TPM, you can say, hey, I would like a storage primary key, and please go ahead and mix in the firmware unique secret that's unique to this version of the firmware. So these keys that you create with these handle values will change across a firmware update. So you want to be aware of that. That's a feature. It's also, something that you need to know when you're thinking about how you're using that key. Okay, so a very important special case of create primary and primary keys is something called the endorsement key. This is the key that you get a cert for when you buy a TPM at the TPM store. So the endorsement key, we use the endorsement primary seed. It's fed in the DRBG along with a particular template, which is essentially the parameters of the EK or the endorsement key for that TPM, and you get access to the endorsement key. So, like I said, when you buy your TPM at the TPM store or eBay, or it's soldered onto your PC or your server, there's actually a certificate stored in there. It's issued by the TPM vendor's PKI, their public key infrastructure. And so when the TPM is being manufactured, the vendor will harvest the EK public key and issue a cert to that. This is important because when you're talking to a TPM, you might be interested in the fact that you're talking to a TPM and not someone running a simulator or trying to fool you. So you want to know that you're talking to a legitimate TPM. You probably also want to know that you're talking to a particular legitimate TPM, etc. So, like our threat model says, like a particularly bad firmware bug could leak anything, including the EK. So how can we trust the TPM again? So plug in this feature, introducing firmware limited EKs. So we actually say, in this case, that the bootloader can generate a firmware limited EK, and it can endorse it with an embedded CA. And the vendor would instead of certifying the EK directly, they would certify the embedded CA intermediate inside the chip that's associated with the bootloader. So that means that sort of on demand on boot, the TPM would produce this firmware EK cert chained off of its bootloader cert. And we can include the measurement of the firmware for people who are interested. I want to be running on this particular TPM, running this particular firmware. If you've heard of this before, it's not a new idea. It's called DICE. It is a standard that's also published by Trusted Computing Group, who are the people who publish TPMs. So that's pretty great. DICE is a generic standard for attesting a low-level firmware using exactly this chained principle. So over on the left side, you can see there's something called a UDS, which is the unique device secret. That's combined with a measurement to produce something called the compound device identifier. And so in our case, that is used to create the device ID key, which is pretty much our bootloader embedded CA. And that's where the vendor's PKI gets plugged in. From there, we can make more measurements, though. We can take the device ID keys, CDI, and mix in some more stuff and come up with the firmware CDI. That creates something that we call firmware alias key, and that's essentially like our firmware limited EK. And then you can walk the chain up as far as you want. You can either keep doing DICE or you can start doing TPM. So yeah, with that, we have a short demo for you all.
So as I say, we've been moving towards TPM, and so I'm going to show TPM firmware running inside our Titan chip. It isn't an emulator, but this would work on real hardware if we had more time to wrangle that. So Okay. Cool. Let's print the EK for this thing. This is not X509, what you'd actually see in a regular EK. This is just our own custom internal stuff. But as you can see, we have the firmware hash in a super readable format. I don't like that. You got the version numbers here elsewhere. So let's try and cool. We sealed using a Firmware Limited owner hierarchy. Here's the resulting TPM structures. We've written that out to a file. Let's try unsealing that. Cool, got it out. Now, time passes, and we review the code and we notice, oh, look at that. That's a very important bounce check for writing NV data into an SRAM buffer, and that is completely wrong. That should be a minus. So let's imagine that that bug can be used to stage whatever you want in internal RAM and corrupt things and eventually pivot to remote code execution and leak everything, including all of the primary seeds. Oh no, what do we do? Well, let's fix the bug. Let's roll out some new firmware. Okay, now since the old firmware was really buggy and might have leaked everything, our old secrets are kind of in the wind. We have to make new ones. So let's start the TPM. Cool. All right, awesome. Now, let's suppose someone decides that now that they know that this vulnerability exists and there's some old signed firmware out there that has this vulnerability, they want to take advantage of it and put it on our machines and use it to crack the new secrets that we just laid down. So this is a rollback. Start the TPM. I'm going to try and unseal that secret. Oh no, integrity check failed. That is not an error caused by the TPM saying, oh, that was for the wrong version, so I'm not going to unseal it. That is the TPM basically saying an HMAC check failed. But if it tried to skip that and proceed to try and do an actual decryption, it doesn't even have the key material available to it to succeed, even if it wanted to, because the firmware, the version unique secret has changed that the bootloader gave out. So, huzzah.
So yeah, just to kind of wrap things up, we think that all code everywhere should be attestable as much as possible because all code everywhere is code and code has bugs. We just need to find and fix them. So in general, making things attestable allows recovery at scale, even in situations like a data center where the computers outnumber you. So the very latest version of the TPM 2.0 library, version 183, came out this March. It introduces new features. So this allows you to recover from severe TPM vulnerabilities, and it kind of ties together TCG DICE with TCG TPM. So our 2-point call to action is, if you're in this room or watching this recording and you're a TPM vendor, please pick up the new version of the standard and please go ahead and implement this feature. If you are a TPM customer or a customer of a TPM customer, someone who builds systems or buys them, start asking for this feature. The TPM library spec is what's called a library, which means that just because a feature is added to the spec doesn't mean every implementation has to pick it up. So, you know, at first, this is an optional feature. We wouldn't mind if it was required in the future, but use cases differ. So if this is something that you care about, you know, let your TPM store or system builder know about it.
Thank you.
Does anyone have questions?
So I don't recall what, if any, capability is required in terms of downgrade protection out of the spec itself. So can you speak? So it sounded like fundamentally in your downgrade attack prevention thing, would you say that that provides sort of a future forward? If people are utilizing this capability, then forevermore, as long as you're using that type of key, you get the downgrade protection for free without reference to whatever the particular TPM maker has for downgrade protection?
Yeah, it's a good question. So downgrade is not the only path towards someone leveraging an old bug. It's possible someone leveraged the old bug and leaked all of your primary seeds. That means in the future, even if you fix the bug, any secrets you make from those primary seeds are completely in the fair game. So this makes sure that you can always be making keys out of secrets that you know that potentially old buggy firmware you don't know about can't have gotten.
Okay. And then one of the most interesting things I found of this was the fact that you said, Google was using Titan custom silicon, and now you're sort of moving back in the opposite direction towards using TPM. How much of that is just internal politics and, the TPM guys won over the Titan guys versus, other more fundamental reasons?
Sure. So Titan has been great and served us very well and will continue serving us very well as a hardware substrate, as a very transparent platform for us to put things on. As our fleet gets more heterogeneous and consists of a mixture of hardware we build ourselves and hardware we want to buy from other OEMs, it gets harder and harder for us to enforce a security posture which requires Titan everywhere. So we are looking at industry standards that are close enough to what Titan already did and seeing what we can do to migrate towards those, and teaching our control plane how to interact with TPMs and SPDM and all these open protocols means that now we can get security, whether it's a Titan under the hood or a TPM like off the shelf. Obviously, we have more confidence in the transparency of Titan is and continues to be very nice for us. But getting a security story on an off the shelf machine is good. So
thank you.
Hey, thank you for the talk. I was wondering, in terms of minimizing the trust in computing base. So, previously we had the bootloader, which was that simple jump to the firmware, and now we're kind of introducing the boot CA, the vendor CA, the whole certificate authority. Wouldn't that enlarge the trust in computing base inside the bootloader?
It does give the bootloader more responsibilities. That is true. However, the bootloader's interface to the outside world doesn't get significantly bigger. It's still not parsing arbitrary external user input. It's just using some internal data and producing a certificate which can be templatized, so you're not actually you should never be parsing X709 in the bootloader for sure. But assembling templatized stuff is not the worst thing to do. Yeah, but it's a fair point. So, carefully auditing these things is very important.
The second question I had, the practicality of, in my doc, I also like the key derivation thing, but the practicality, inside the TPM. So, let's say the bootloader is basically has this device unique secret, and we were sure that the firmware version, which is buggy, cannot leak it somehow. That means the chip itself has some kind of isolation between the firmware and the bootloader, which maybe cheaper devices do not have. Let's say, if I load the firmware, I get control of everything. What are the hardware requirements for my buggy firmware not to be able to leak that bootloader unique secret? Does that make sense?
That's a very good question. So I think at the most basic, you can get really complicated and fancy with this stuff and just have all your keys runtime in hardware that can never be leaked. But at the most basic, I think it requires just some persistent data that can be read by the bootloader that can then be soft locked out for the firmware that runs after.
Okay, thank you.
Mm-hmm.
Sorry, a nitpick. Is it fair to say that it doesn't actually provide downgrade protection? It provides rollback protection, because you could always put the next thing on, but it just means you can't go back and get secrets from previous ones.
Sure. Yes, this does not prevent you from rolling your firmware back and having it do things. It just prevents that firmware from landing there and stealing all your secrets. Yep.
Any other questions? All right, let's give them a round of applause. Thank you so much.